Let's do problem 41 from chapter 8. It's on page 244. And it looks like this. Let's zoom in on it. What are you talking about? Okay. That's Emmanuel Lopez talking, and so really shouldn't listen. All right. So we have a single conservative force acts on a 5 kilogram particle with this equation, 2x plus 4 in newtons. Describes the force where x is in meters. As the particle moves along the x-axis from 1 to 5 meters, calculate the work done by this force, the change in the potential energy of the system, and the kinetic energy of the particle at x equals 5 meters if its speed is 3 meters per second at x equals 1 meter. Whew. Okay, so where'd it go? Well, let's zoom back out. So let's write down what's given. We have this force, and the force in the x direction is equal to 2x plus 4 newtons. Now x, it says, is in meters, so this 2 must be in newtons per meter. This is like a spring constant right here. This 2 is acting just like a spring constant. And then, and the mass of our particle is 5 kilograms. And it says the particle is moving along an x-axis. So let's draw an x-axis here. And it looks like all our motion is between 1 and 5 meters. So I'll just go 1, 2, here's 0. 1, 2, 3, 4, 5. And so we're starting, so x initial is 1 meter. So we're starting here. Here's our particle. And this force is doing work along the x-axis. So here's x initial equals 1 meter. X final equals 5 meters. And what are we trying to find? Well, for part A, we want to know what is the work done by this force. And then B, the change in potential energy of the system. So we want to find delta U. And for C, the kinetic energy of the particle at x equals 5. So we want K final. That's, at x equals 5 meters. And it said if its speed is 3 meters per second at 1 meter. So when it's at 1 meter right here, V initial is equal to 3 meters per second. So we'll just add that to what is given. So this is our situation. So let's go ahead and solve it. Well, this is part A. We just want to know how much work is done going from here to here if this is our force. And I'll go ahead and start with the most basic definition, F dot dr, right? But here, our force is, well, this little subscript means it's Our force is all in the x direction. It's a function of x, and my displacement is along the x-axis. So this turns into fx dx. I mean, everything's along the x-axis. So we can take this thing and just do that to it, simplify it. So let's put in our function for the force, 2x plus 4 newtons. Okay, dotted with, well, we can dot it, but we don't need the dot product anymore because everything's along the x-axis. We'll just multiply it by dx, and we're going to go from 1 to 5 meters. Well, this is an easy integral to do. And I expect everyone in here to be able to do this integral. It's just the power rule. That's the one you really need to know, is the power rule. So we have 2x times x. Well, what is 2x times x? That's 2x squared, but you have to remember to divide. The power rule says divide by the new exponent. And then plus, well, what is 4 times x? It's 4x. We're going from 1 to 5. Okay, so now I just need to plug in my final value of x. 2 times 5 meters squared over 2. Now, by the way, this 2, like I said, it has units of newtons per meter. It has to. And plus 4 times newtons times 5 meters. Okay, so that's what I get when I plug in my final value of x minus my initial value of x, 2 newtons per meter times 1 meter squared over 2 plus 4 newtons. This is 4 newtons times 1 meter. So we just have to do the arithmetic now. Well, this 2 cancels. This is 25 plus 20 is 45 joules. Minus, well, this cancels. This is 1 plus, well, what is 1 plus 4 is 5, so it's minus 5 joules. So we're looking at 40 joules. Is that right? Is that what the book got? Okay. So that's the work done by this force. This force is a function of x. We have to integrate along x. And there we go. Now, it says that this force right here, it stipulates in the book, it says a single conservative force acts on a 5 kilogram particle. The equation is for the force is this. So they're telling you that this force is a conservative force. So for part B, you say when a conservative force does work, you are losing potential energy. The work done by a conservative force results in a loss of potential energy. So if you want to find delta U, well, delta U is equal to the negative work done by the conservative force, and so that's going to be negative 40 joules. Now, if this doesn't make sense to you, think about a spring, and really this is a spring with a little constant added to it. When a spring does positive work, well, where did that energy come from? It came from the potential energy stored in the spring. When gravity does positive work, when you drop a stone from the top of a cliff, the force is down, the displacement is down, so gravity is doing positive work. But you're losing gravitational potential energy when that happens. So this little thing right here makes sense. Okay, and we're going to deal with electric potential energy next semester, and it's going to follow from that as well. So that's all you need to state right there for part B. Now, for part C, the only force doing work right here is a conservative force. So now the equation I like to use is this. The work done by non-conservative forces will change the mechanical energy of your system. And that's just a statement of fact. But there are no non-conservative forces doing work in this problem, which means the work done by non-conservative forces is equal to 0, which means my change in mechanical energy is 0, which means my initial mechanical energy must be equal to my final mechanical energy. Well, what is the initial mechanical energy in here? Well, if I E initial is the initial kinetic energy plus the initial potential energy here, and that will have to be equal to the energy at my end state okay. So so what we need to do is solve for the final kinetic energy, because that's what I'm looking to find here. So K final, the final kinetic energy, will be equal to the initial kinetic energy plus U initial minus U final, right? All I did was add this to the other side. Well, this is U initial minus U final is basically negative delta U. So I want to subtract from it. So this is K initial minus delta U. So let's solve for K final now. K final is equal to K initial, but that's 1/2 the mass, which is 5 kilograms, times the initial velocity squared, minus delta U. Well, delta U is negative 40 joules, so minus negative 40 joules. Now this makes sense. I'm adding it. It's going to be this force up here. This force is pushing along here. It's going to be going faster and faster and faster. It's doing positive work. You can also think of this in terms of the work energy theorem. The work done by the net force will result in a change in kinetic energy. You can also use that. Actually, that might be a little easier than the way I've approached it here. But in any case, what is this? This is 9 times 5 is 45. 45 divided by 2 is, what, 22.5 joules plus 40 joules. So the final kinetic energy should be 66.5 joules. Or, I'm sorry, 62. Why did I do that? .5 joules. And is that the right answer? Is that the answer they have in the back? Check my work. Question authority, people. Is that right? Is it? Are you just saying that to make me stop asking? Look it up.
Oh, yeah. Huh.
The answers are in the back of the book. Good grief. This is number 41.
This table of contents is too big. I'm scared.
fingers are so cold I can't change the thing. 40, negative 40, oh, 62.5. That is correct. I did it right. I feel good about myself. My self-esteem has been confirmed. Okay, my self-worth, is intact. So there you go. Number 41.